Welcome everybody to the first webinar of 2025. My name is Nate McCown. I am a space systems engineer at AI Solutions, and I am the technical support team manager. Today, I'll be walking everyone through FreeFlyer familiarization. So we'll be going through FreeFlyer at a high level, give some introductory information about the company itself, as well as provide some additional resources for new users to get started with the tool. A few notes at the top here. Before we begin, all attendees will be muted and cameras will be off for the duration of the webinar. We are recording this webinar and we'll provide the slide deck afterwards along with a link to the YouTube video. If you have any questions that you'd like to ask, please use the QA function and the team will pass those along to me. Lastly, if you want to talk to other participants or AI Solutions sales staff, please use the chat function. We have two representatives of the sales team in here. So if you have any questions about licensing or how to get FreeFlyer, they would be happy to provide some detail. A little bit about the company. So AI Solutions is a privately held company, and we've been operating for a little over 25 years, actually coming up on our 30th year. We have offices headquartered here in Lanham, Maryland, close to the DC area. We have offices also in Colorado Springs, California, Huntsville, and a larger office down at Kennedy Space Center in Cape Canaveral. You can see some core capabilities here of the company, which include FreeFlyer and other space applications. There's a list here of certifications and awards, but if you want more information on that, you can find details on our site. So let's get into what we're here for. FreeFlyer provides end-to-end support for the full satellite mission lifecycle. Design mission parameters, refine requirements, and study constraints. You can perform analyses and trade studies to model optimal flight plans and contingency scenarios. You can integrate FreeFlyer into operational ground systems and automate flight dynamic system functionality. We'll talk more about all the different capabilities throughout today's webinar. But before we do that, let's talk briefly about the heritage of the tool. Here on the left-hand side, you can see the Mission Control Center down at Johnson Space Center. That's just one of the many customers that use FreeFlyer. We've been operating for 29 years, as I mentioned, and we have supported over 225 satellite missions. Some more notable missions here on the right-hand side include the International Space Station, more recently, NASA's James Webb Space Telescope, and others such as SNC's Dream Chaser, and the Artemis program out of Johnson Space Center. Not only do we have these 225 missions under our belt, we also have customers that include NASA, the government, commercial, and the primary focus of today, which is academia. We're in universities all across the globe and looking to add more. So let's talk about how we get started with the tool. Here's a little agenda for what we'll be discussing, highlighting first the FreeFlyer capabilities at a high level, then navigating FreeFlyer, the spacecraft object, which is the core object in the tool, FreeFlyer script essentials, the step command, lists and formations, procedures, generating basic output, and the output window objects. First things first, under the analysis umbrella, you have spacecraft propagation and trajectory design, coverage and contact analysis, communications and RF link analysis, maneuver targeting and optimization, collision avoidance and conjunction assessment, attitude modeling, terrain line of sight and viewshed analysis, and orbit determination. Throughout the entirety of today, we'll be talking about the flexible output and interfacing side of FreeFlyer, which includes the native scripting language, the reporting, plotting, and products generation portion, 2D and 3D visualizations, and the runtime API, which is your avenue to integrate FreeFlyer into your ground system. Starting with spacecraft propagation, FreeFlyer propagation lets users specify high-fidelity numerical integrators. We offer SGP4 and SGP4XP integrators, ephemeris read-write capability with interpolation, industry-standard gravitational and atmospheric models, user-defined space environment forces, and spacecraft physical properties, including flat plate modeling for SRP. We support modeling unlimited number of spacecraft simultaneously. We'll talk more about the formation object in FreeFlyer script a bit later, but this is how you would model a constellation or formation using FreeFlyer. We support all orbital regimes, including LEO, GEO, highly elliptical, cislunar, and deep space. And then we also have tools for relative motion, for rendezvous and proximity operations, and formation flying. Here on the left-hand side, you can see an example of the MMS mission, which was flown out of NASA Goddard and supported by our folks here at AI Solutions. This is a 4 spacecraft formation modeled in FreeFlyer, but as mentioned, you can fly any number of spacecraft using the tool. With regards to coverage and contact, there are hundreds of predefined ground stations with accurate masking profiles, and you also have the ability to customize your own. This can be either on Earth or in any celestial object built into FreeFlyer, or even a custom celestial object if you're looking to model something like an asteroid. You can easily gather visibility, azimuth and elevation, range and range rate, in-cross track and along track, and coverage and revisit statistics. In the bottom right-hand side, you can see an example of filling a region, Canadian region in this case, with a point group and doing revisit statistics using a constellation with sensors attached. Contact methods allow for contact times between spacecraft to spacecraft, spacecraft to ground stations, spacecraft to custom 2D and 3D regions, as shown on the right, or you can do chains, shown in the top right-hand corner, as a visibility calculator, which is going from 1 ground station to 2 spacecraft to a 3rd ground station, modeling that link analysis. Speaking of communications, we have an RF link object for two-way communications analysis. You can define transmitters and receivers using either ground stations or spacecraft objects. You can import or define antenna gain patterns, as shown in the top left corner here. We support both phi theta and theta phi antenna gain patterns. And you can calculate parameters such as free space path loss, EIRP, signal to noise ratio, link budget or link margin, as well as received and transmitted power. We are adding on to this capability in FreeFlyer 710, which is slated to release later this year, and we'll be including an optical link object for more refined analysis. On to maneuvering and targeting. FreeFlyer supports impulsive burns, which is a delta V magnitude and direction, finite burns, which is a burn duration and direction, as well as full propulsion system modeling for chemical or electrical, which includes low thrust systems. So depending on the hardware that you're going to be having on your spacecraft, you can really get down into the weeds and produce a high fidelity result from FreeFlyer by modeling your propulsion system. Maneuver targeting, we include a differential corrector targeting system. You can target impulsive or finite burn parameters to achieve desired mission states. You can target multiple parameters in a single sequence. This could include things like raising the semi-major axis, as well as targeting a specific inclination. And you can automatically generate maneuver command reports, including fuel consumption and thruster sets. Note that FreeFlyer is used operationally for maneuver planning, calibration, reconstruction, and estimation, so you can have faith in the results that you are receiving. On to optimization. FreeFlyer supports a generic optimization capability, which allows the user to define any objective function. This includes any number of optimization variables, number of constraints, as well as equality or inequality constraints. The ability to specify scales, as well as specify known derivatives, which the Jacobian, as well as a gradient of the objective function if you're looking to speed up the performance of your FreeFlyer mission plan. We support 3 industry standard optimization engines. Those are SNOpt, NLOpt, and IPOpt. The only one that requires additional licensing is SNOpt, as that license will be user supplied, but the other 2, NLOpt and IPOpt, are both free and built in natively to the tool. More recently in FreeFlyer 7.8, we added support for collocation-based optimal control. This allows for segmented trajectory arcs, ballistic, simple thruster, and ideal solar sail control models, and really built out the support for continuous thrust maneuver modeling. Here on the left, you can see a few examples. One, which is a GTO to GEO transfer, where the final trajectory or the final orbit is the green, and the transfer trajectory is marked by all the white vectors. Those are going to be your thrust arcs. And you can see that we started in that initial orbit in Leo. I should note all of the images being shown here come from sample mission plans, which are provided for free in your FreeFlyer installation. And we'll talk more about where to find those in a bit. With regards to attitude modeling, you have full customizable attitude motion model with 6 built-in reference frames, or the ability to define custom coordinate systems. The 6 built-in frames are shown below, and the attitude systems are defined by Euler angles, quaternions, attitude matrices, or a spinner. Lastly, you can define a motion based on an attitude history file. So if you have an AHF from a tool like STK, you can load those in directly into FreeFlyer for use within the tool. In the top right, you see an example of slewing a spacecraft for contact analysis. And in the bottom right is a simple rendezvous, which is shown with those axes, the orientation axes, which are defined in FreeFlyer natively. For interplanetary analysis, you have B-plane targeting for hyperbolic trajectory arrival. You can create custom celestial objects. These could be things for analyses for asteroids, different moons, as well as customize their properties. They have propagators built in. You can use a two-body, you can pull a spice ephemeris, or you can use a definitive ephemeris. You can assign the flattening coefficients, the gravitational potential field, as well as the attitude properties. And if you're looking for nice visualizations, you can add texture maps as well. They support inertial and body fixed reference frames built in for every celestial object. And we have the ability to read and write SPICE files natively. Lastly, as I mentioned in the coverage section, ground stations are able to be used on any celestial object for advanced OD via ground observations or TDRS-like relay observations. In the top right, we have an example of a 3D model loaded into FreeFlyer to represent an asteroid, and then you can see the orbit in which this spacecraft is going around that asteroid. For terrain analysis, FreeFlyer supports any raster terrain file format supported by GDAL for line of sight analysis. It's compatible with public and restricted access data in many formats and resolutions. This is tested with publicly available data, including GTOPO 30, SRTM, and the national map, which includes resolutions as low as 3 meters. You have the ability to load global terrain or a specific region of interest. And you can load from a local file wherein there is no terrain server required, so no internet connection is required to do this analysis. This is helpful for visibility of any combination of assets, such as GPS coverage analysis in mountainous terrain, a ground vehicle following a route through a canyon or over a mountain, geocomlink connections, LEO imaging visibility, or viewshed analysis. On the left-hand side, you can see a drone tracking a ground vehicle through a terrain or through a mountainous region, and the terrain here is visualized using a graphics overlay. On to orbit determination. For the estimators, we support batch least squares, an EKF and UKF, so an extended and unscented Kalman filter, as well as a square root information filter. There are smoothers available for EKF, UKF, and SRIF, and 7 natively supported observation types, with the ability to also parse in custom measurements. You can do spacecraft to spacecraft, ground observation, GNSS, which supports either GPS or Galileo, as well as TDRS. The estimated objects include spacecraft, ground station, or thrust events, as well as the subsystems on board the spacecraft, such as the sensors, receivers, and transponders. You have the ability to do covariance propagation, analysis, and visualization, as well as multi-spacecraft estimation. On the right-hand side, we can see 2 different things. The first being covariance visualization. We have a spacecraft with the covariance air ellipsoid modeled as a graphics overlay. And in the top, you can see multi-spacecraft estimation with some geobirds, as well as focusing on the cloud of LEO spacecraft around the Earth. FreeFlyer supports collision avoidance in SSA and SDA. So automated collision screening for any number of spacecraft. This could be one versus all screening via TLE full catalog or subset. Conjunction assessment for one versus one via conjunction data message integration or ingestion. There are built-in methods for each conjunction event. So this includes the time closest approach, or TCA, probability of collision, which is P sub C, the along track, cross track, and radial miss distances, the ability to do Monte Carlo state sampling, and 3D conjunction geometry analysis and visualization, as well as maneuver planning for collision avoidance. A great mission plan I'll point you to is on the home screen, which is close approach maneuver, which demonstrates reading in a conjunction data message, propagating to the time closest approach, and then performing a targeting sequence for a risk mitigation maneuver. This is fully scalable for the full catalog for SSA and SDA analysis, and we include support for rendezvous and proximity operations, modeling docking, and satellite servicing. Last slide before we take a short break. The FreeFlyer Runtime API provides interfaces for tightly integrating FreeFlyer into external applications. The Runtime API supports applications written in C, C++, C#, Java, MATLAB, and Python. It's available in both Windows and Linux platforms. And one application can execute mission plans in series or in parallel, both synchronously or asynchronously across multiple FreeFlyer engines. The runtime API calls can also include FreeFlyer visualization. So this really provides you the ability to use FreeFlyer's astrodynamics engine in a host application that you already have built out, take all the space math and the visualization capabilities, and then take all the work that you've done in any of these other programming languages to pull the necessary details in. So let's talk now about the tool itself, navigating FreeFlyer. When you first open FreeFlyer, you'll see the home screen. We'll briefly go through what the contents are here. In the top left, we have the menu bar. This is just to create new mission plans, the ability to go through your user preferences, or even check out the help documentation. The second side, staying on the left-hand panel, you can create a new mission plan or browse sample mission plans. We have over 225 sample mission plans covering everything, all the objects in FreeFlyer, demonstrating things from the lowest fidelity to the highest fidelity, as well as including visualization capabilities as well. To learn more about the tool, outside of going to webinars like this, you have a few helpful links here. So what's new in FreeFlyer will cover all the details of the most recent release. The FreeFlyer features overview will show you all the different capabilities the tool supports. Getting started with FreeFlyer is going to show you how to build out your first mission plan. Then there's a fundamentals training series, which is available on YouTube with a helpful link on the screen here. Your more recent files will open up here on the left-hand side. And in the middle of the screen, this is where you'll find our flashy mission plans. So these are some of the more complex mission plans that we have built into the tool itself. Things like close approach maneuver, which I mentioned earlier, James Webb Space Telescope visualization, some other really cool ones like the SLU maneuver mission plan or the constellation coverage mission plan. All the new mission plans are mission plans that are with new features. So each release, we will update this list, will be shown at the bottom of the middle. And on the right-hand side, you can find contact information for the tech support team or the sales team, as well as a tip of the day, which are written by the tech support team to help power users better understand the tool. Once you've created a new mission plan, you'll be taken to the control screen. On the left-hand side, you have the object browser, which is where you'll add objects and you can open up any object dialog to change properties that you would like to match your system. On the right-hand side is the script elements. These are nice drag and drop elements. This is how you can build out your mission sequence, which is here in the center of the screen. The mission sequence is where you'll build out the analysis you're looking to perform. So in this case, we have a while loop. We're going to propagate a spacecraft for one single day, and we're going to update a view window. A view window can be in multiple different viewpoints, which we'll show later. But for right now, it will just show a simple example of building out a simple propagation loop. So I've got my home screen here. I'll click New Mission Plan. Right now, I've got nothing, so I'm going to create a simple spacecraft. I'll go to Add, Spacecraft. And just for the purposes of this demo, I'll simply drag a while loop in, a step command to propagate the spacecraft forward in time, and I will drag a view command in. You can do a simple syntax check. The status message shows that I've passed. And I'll just run this mission plan as is. We'll talk more about the visualization capabilities in FreeFlyer, but what you can see here is I can replay, I can start back at the initial state, I can slow this down, I can speed it up, and I can even choose specific epochs if I'm doing some QA with maybe an output file for coverage or something like that. You may notice that it's a bit choppy in this first visualization. That's due to the default 300-second step size, but those are things that can be fine-tuned as you continue to use the tool. As we saw with the navigation bar, the green check is a simple syntax check. The play button allows us to start the mission plan or pause it, as well as break into a debugger. And then you have other commands like the undo and redo buttons, which allow you to undo or redo something that you've undone. And lastly is the status message. So in the bottom left, if your mission plan has a warning or an error, you'll receive that status message upon syntax check. You'll also get the status message is mission plan complete if you've run your mission plan successfully. And you can get a run time, so a run duration in seconds in the bottom right-hand corner. Additionally, the freeform script element, which we'll talk more about in a bit, is this blank screen, blank text pad that's shown that allows you to utilize FreeFlyer script, and all the script elements can also be converted into FreeFlyer script. So when we talk about becoming a power user of FreeFlyer, what we oftentimes notice is people shift from using the object browser and script elements to doing everything in script. Script being freeform script or FreeFlyer script rather. So inside the freeform editor, this is where you can create and customize FreeFlyer script. We'll demonstrate some more examples in a bit. Lastly, we'll show the output. So the output screen will create a new workspace tab each time the mission plan is run. The status message and run duration will be updated, and you have the ability to navigate between the control screen and output screen. We saw a little glimpse of the replay toolbar, but the replay toolbar at the top here is what allows you to choose playback speed, play forwards or backwards, jump to specific frames or epochs, step frame by frame, and many more things. All right, so we'll jump into the spacecraft object. This is the core or fundamental building block of your FreeFlyer analysis. The spacecraft object provides interfaces for orbit and attitude propagation, physical bus and subsystem modeling, coverage and contact analysis, maneuver modeling, and orbit determination. We'll start by looking at initial orbit state configuration, attitude model setup, physical properties, and force model and propagator settings. All right, so setting the initial state. The spacecraft's initial state defines the orbit shape and orientation with respect to its central body. You can define the epoch, central body, orbital elements, and reference frame all from the orbit page. So when I double click to the spacecraft object, you'll notice that I have this object dialog. We'll go through all these pages individually, but first, this is where I have the ability to set my initial state. Right now, I've got January 1st, 2020, which is just the default epoch. I'm doing a, looks like a Leo orbit around Earth. So I also have the option for element types. So the default is Cartesian. You can change to something easier like Keplerian. I'll just show the orbit preview window here on the right-hand side. I changed the semi-major axis to 10,000. You can see the preview is replicated here. And then you can also change the reference frame. So the default reference frame is going to be ICRF. You have the option for a few others, and you can find details on all of that through the help documentation. Lastly, I should mention at the bottom of the screen is an orbit wizard. So the orbit wizard allows you to create a custom orbit or load orbit state data from a file. These custom orbits include things like a pre-canned Molniya orbit or a sun sync orbit. And there's interfaces to help navigate learning how to create those types of orbits in FreeFlyer. Onto the attitude tab. The spacecraft's attitude can be specified using a custom model or an attitude history file. Here on the attitude page, you can specify a custom model with a reference frame and attitude system. As mentioned previously, the attitude systems include Euler angles, quaternions, attitude matrix, as well as spinner. And depending on which attitude system you pick, that will also demonstrate or show more properties that you have the ability to change. So in the case of Euler angles, you can choose the rotation sequence, and then alongside that, you can choose the Euler angles themselves, as well as the Euler rates. If you choose to use an attitude history file, you simply browse to the file, and we support two different file formats here, the FreeFlyer attitude history file, which is a .efim, as well as a STK attitude history file, which is a .a file. The spacecraft's epoch determines what attitude will be selected or interpolated from the AHF, and FreeFlyer will throw an error if the spacecraft's epoch is not contained within the bounds of the AHF. Onto the physical properties page. On this page, this is where you'll specify the physical properties of the spacecraft. This includes the area properties, such as the drag area, lift area, SRP area, as well as the coefficients of drag, lift, and reflectivity. You also can set the mass, the center of mass, and the moments of inertia relative to the spacecraft body coordinate system. I'll quickly jump to that page in FreeFlyer. And I do want to call out the drop-down arrows, which I may have missed earlier. So in the case of drag area, all the default units are shown here on the right. You do have the ability to change those units if you choose to do so, and FreeFlyer will natively make that conversion for you. All right, on to some important stuff, the propagator. So propagation using an integrator. As we saw in our example, spacecraft in FreeFlyer are propagated using the STEP command. Each spacecraft can be propagated using any of FreeFlyer's built-in integrators or by using an ephemeris file. To use an integrator, you set the spacecraft's motion source to integrator and choose the integrator type. The default is Runge-Kutta 8.9, but we do have lower fidelity propagators such as 2-body or J2 mean, and we'll quickly take a look at those. Before we do that, actually, let's talk briefly about the step modes. So choosing the integrator step mode, you have two options. The first being fixed step size. A fixed step size ensures a fixed data output interval. This could come with possibly slower operation speeds if you're doing something like a really low step size for an interplanetary trajectory, but the user specifies that step size. So a positive step size would propagate forwards in time, a negative step size would propagate backwards in time. The alternative is a variable step size. This allows FreeFlyer to increase and decrease the propagation step size based on the specified air tolerance. This could potentially improve speeds, but data can only be reported after each step, so there's no guarantee that it's at a constant interval. That relative air tolerance is offered in both step modes, and it's intermediate integration steps that are taken behind the scenes to ensure that the local air never exceeds the specified value. So let's quickly take a look at the propagator page. So we're focusing right now on the integrator source, or the motion source set as integrator. You can see the full list of all the integrator types available, including relative motion, which is HCW, SGP4 if you're working with a TLE, as well as some additional options which are offered. I do want to highlight the documentation briefly. So on what I've done here is I just hit the help button. So in terms of documentation, the easiest way to get to it is to find the object or specific page you're looking for, and there should be a help icon, or you can hit F1 on your keyboard. So by clicking help here, it automatically takes me to the spacecraft propagators page. And if you're unsure of what propagator to use or what to use, then you can refer to this table, which gives you characteristics, the accuracy, speed, and what the recommended use cases are for each individual one. So I mentioned just a moment ago, the default is Runge-Kutta 8.9. So you can see that is what we're comparing against for the rest of the integrators. All right. Moving along, we'll talk about force modeling. So FreeFlyer lets you control the forces acting on each spacecraft, the gravitational force from any celestial body, Earth atmospheric forces, solar radiation pressure, and user-defined forces. You can see all the available bodies that are built into FreeFlyer, and as mentioned, you can, if you create a custom celestial object, that will show up in the available bodies list as well. So that's where you would add the gravitational potential file that you might have on hand. SRP is outside the available bodies, but you can check that box. The default is a spherical cannonball method, or cannonball model rather, and there is an option at the script level to do flat plate SRP modeling. You can find some examples of that in our spacecraft propagation folder, as well as more information on the available data files, which we'll talk about here in a bit. For the gravitational forces, you can model gravitational forces for any of those built-in or user-defined celestial objects. You simply check the box in the list of available bodies to turn on gravity effects, and then you can configure the model for each body separately. These range from simple point mass to zonal and tesseract potential field with solid tides. So you can go from low fidelity all the way to high fidelity just in that drop down for field type. You can use your own gravity model data or the data files that come with FreeFlyer. I won't go through all of these. These are available in the data files folder. The default for Earth is EGM96, but you can see that we also offer some additional models for Earth, some for the Moon, some for Mars, as well as Venus. The included solid tide model is love numbers for Earth up to degree and order of 3. For the atmospheric forces, you can model both lift and drag due to Earth's atmosphere. We support a number of atmospheric density models. These include MSIS 2000, 90, and 86, as well as Harris-Priester, Jacquard-Roberts, and Analytic. You can find more detail on all of these density models in the appendix of the FreeFlyer help file. We'll talk more about the subsystems and orbit determination settings later, but for now, we'll just briefly build out a sample mission plan. So if you'd like to, you can follow along. As mentioned, this is recorded and I will be sharing the slides. So if you'd like to just hold off until after, that's perfectly fine. We'll be doing it here live on the screen as well. So in this case, we're going to be kind of building off that initial mission plan that I started. We'll create a spacecraft object, propagate it for some duration, and add a few outputs. So the plan is to create a spacecraft object, we'll propagate it for 1 day, add some output, and just simply practice navigating the FreeFlyer interface. So if you're following along, you can start by creating a new mission plan and saving it. We'll save it as FreeFlyer Familiarization, add a spacecraft object to the object browser, drag a while loop in from the list of script elements, drag a view command and a step command inside the in the while loop, and then run the mission plan for basic simulation. Once we've done that, we can go ahead and drag the plot command inside the while loop. We'll double click on the plot command and edit it, and we'll show the spacecraft's height on the y-axis with the elapsed time on the x-axis. And lastly, we'll run the mission plan a second time, and we should see that we have 2 different workspaces. The first shows the 3D view. The second will also include the plot. You can save your progress, and we can continue building on that later. All right, so I'm just going to start from scratch in case anyone's following along. So I can hit create a new mission plan. And on the left-hand side, this is our object browser, so we'll spend some time navigating. At the top level, we have our 4 most commonly used objects. This is the spacecraft, the ground station, a variable, and a view window. Under all alphabetical, this is all the objects that are available through the object browser. You can see we have some lists which group things together. So under spacecraft related, you'll find spacecraft, the formation, which is a list of spacecraft, ephemeris, some different maneuver types, impulsive, finite, as well as an outgassing event. Under output, you have all your different output windows that we'll talk about later, and you kind of get the theme there. So we'll go ahead and add a spacecraft. We've played around with the object dialog. We've seen if we change some orbital elements, we get that reflected in the orbit preview window. Since I didn't open it earlier, I'll briefly open the orbit wizard. And for the purposes of this example, I'll just use a sun sync orbit. You can see here I have some options. For the independent variable, I could set the inclination or the semi-major axis, and that will determine what my calculated values are here on the right. So just to reflect that, I'll just jump this up to 8,000. You can see that the inclination changed and the calculated values. And then I could also change things like the mean local time, the node at the crossing, as well as things like argument of perigee and mean anomaly. Hit finish. You can see my new orbit here. It automatically snapped into Keplerian and reflects the choices I made. You're welcome to use a default spacecraft in this case. We will just build out the rest of the script through the script elements. So I'll drag a while loop in, I'll drag a view command in, and I'll drag a step command in. All right. So this is similar to the example I showed a bit earlier. We have a while loop. We're going to propagate for 1 day. I'm going to view the spacecraft, and I'm going to step the spacecraft. So stepping will propagate the spacecraft forward in time, and while it's propagating, I want to visualize that spacecraft. If I wanted to change the duration, I can simply click on the while loop, and I could change the value from 1 to say 0.5, or you could even change it to be a shorter, you can change the time span units to reflect the propagation you're looking to do. So I'll run this. We can see our orbit. So while we're navigating the tool, I'm going to quickly go through a few things. We have some different view modes, which we'll talk about in a little bit. But you can see I have a 2D map. I can do something like a celestial sphere, which isn't very relevant in this case, a star map, or rotating pulsating view. For the view mode, I also have an option for the reference frame. So in this case, I have my ICRF, my inertial frame, versus a body fixed frame. So you can see that. And I can zoom in using the right click, zoom out, pulling it towards me. I can pan left or right using the left click on the mouse. And we'll talk about output windows and how customizable they can be when we're using the actual output window objects. I'll quickly drag in a plot command to add some additional output. The default here will be spacecraft elapsed time and the semi-major axis on the y-axis. I'm going to change this to be the height. So I double click to open up the plot. I'll click the drop down for the y-axis. And instead of scrolling through the entire list here to find height, I will simply hit H, and that will snap me to the first property that starts with an H. So one thing to note, it is just the first letter. If you start typing HE, it'll snap you back to E. You can add more series on the y-axis by clicking this More button. And the script is going to be reflected in this script preview at the bottom. So as we talked about earlier, as you make that transition to become a more power user, you might be more interested in using the scripting language. So you can learn as you develop those skills through these script previews, which you'll notice throughout the mission plan. So I'll just run it again. We should see the same 3D view, but now we also have this plot. So when it comes to plots, there's a number of different customization options through the all output properties. This is custom plot titles, your axes, as well as the colors that are used. These are also available through the plot window object, which we'll cover in just a moment. You can choose to mark data points or show data labels. It can get a little busy depending on the analysis you're doing, but the mark data points is certainly useful. And then you can add some additional coloring through the interlace direction. If you're interested in specific points, you can click left on your mouse and drag to focus in on a specific area. And if you zoom too far in, you simply right click and that will snap you back to the initial configuration. All right. So I'm just going to save this off since I'll share it. And we'll keep going. So when we talk about script essentials, we're really going to be talking about the power of FreeFlyer script. And the real power here is it gives you unlimited control over every aspect of your simulation. You can create complex logic to model mission unique scenarios and calculate parameters that aren't natively built into FreeFlyer. Some FreeFlyer features are not available through the object editors or script element editors and can only be used inside freeform scripts. And then also the autocomplete and syntax checking make scripting really fast and easy. So it's a pretty easy language to learn. If you have any experience with MATLAB, it is an object-oriented scripting language and oftentimes referred to as space-based MATLAB. So you can pick it up relatively seamlessly. As we showed, you can get started by dragging in a freeform section into the mission sequence. When we're talking about autocomplete, you'll see a drop-down menu of options as you type. And the right-click context menu provides very useful resources such as go to definition, find all references, or go to help file. So I'll just pull up this example again really quick. To learn FreeFlyer script, let's say I've built out my entire mission plan. I've got this whole block highlighted. I can right-click and convert to freeform. And here I can see exactly how I would have scripted this up. So let's just quickly show how the autocomplete works. So in this case, I'm going to type out, I'd like to plot something with the spacecraft and then have a second series. So I'll say PL, you can see the command plot, and then spacecraft, which is an object that I created, spacecraft 1. I can hit enter or tab to autocomplete. On the X, I want the elapsed time. I typed EL, enter, and then say I just want the Cartesian X. So let's do spacecraft 1.x. Simple as that. If I wanted to learn more about what this spacecraft X is, I can right-click, I can go to the help file, and it will automatically take you to what you're interested in. So the syntax to create an object is the type and then an instance name. So if I'm trying to create an object called spacecraft1, I would type spacecraft and then a space and then give it some name. So in this case, it's spacecraft1. Ground station, call it GS. Variable for max altitude. And then FreeFlyer objects can have properties and methods associated with them. Properties can have either read and or write access. An example here is the spacecraft.semi-major-axis, or another one would be what I just showed, spacecraft1.x. Methods, on the other hand, can have more than one overload so that you can pass different combinations of arguments. So in the case of contact, spacecraft to any number of objects. So spacecraft.contact ground station 1, or spacecraft.contact region 1, or you could even do another spacecraft. But there's different options, and I can show what that looks like in the help file as well. So if I wanted to do a contact, I could say something like report spacecraft1.contact. So I want to learn more about what this is doing. You can see the different options or overloads that are available to me. So I could do a cone defined by latitude, longitude, height. I could do a ground station, a point group, a region, another spacecraft. There's a bunch of different options. And if I wanted a script example for how to do a specific one, I would just click in and you can see the syntax down at the bottom of the screen. If you're looking for more detail about a specific property or method, you can hover the mouse over the property to display that information. So you can see the description, the type, so if it's an array of a variable, if it's a variable or a time span, what type of access you have, so if it's read-write or if it's just read-only, the default units, as well as the default value. When you're calling a method, FreeFlyer displays detailed information about each method overload and argument. So if there's a method that has multiple parameters, then you might think you would get lost when you're typing it out, but FreeFlyer will keep up with you and tell you what that next object should be or what that next property should be. And that way you can usefully go through the method overloads. Speaking of useful shortcuts, enter or control space will finish a partially typed script element, and then control shift space will reopen the method description window if you've closed it incidentally or if you stop typing. So just as an example of that, the contact, if I scroll through these. I could close it, and then I can reopen it. Just like that. So we talked about FreeFlyer objects. We mentioned briefly the subsystems associated with the spacecraft earlier. Those would be referred to as child objects. So child objects have their own properties and methods that are accessed through the parent object. We'll use the example of a sensor, but here we can see the hierarchy. The spacecraft object is our parent object. All of our subsystems are here in green, so propagator, thrusters, tanks, sensors, which we're focused on. So to access that sensor, I would go spacecraft1.sensors0 because FreeFlyer is 0 indexed. And then I would have access to all the properties and methods of the sensor child object. So here we have the spacecraft sensor1.cone-half-angle. So that's true for any child object. You must first go through that parent object. For syntax examples for the most common flow control statements in FreeFlyer, we have a while loop, which we've seen is oftentimes used with propagation, a for loop, which would be used for iterating through a loop, and then we have if statements or conditional statements, so if, else, as well as end. We also support try statements. These are used to suppress errors, switch case statements, break and continue statements, pause and stop commands, while stepping and while maneuvering commands. And one trend you may have noticed is every line of FreeFlyer script must end with a semicolon. You can create comments using the double / or / asterisk comment. You can create block comments using the second syntax, but this is very useful when you're sharing your script amongst others if you want to comment your code appropriately. We'll briefly go through the basic data types and functions. So the basic data storage types in FreeFlyer are variable array matrix objects, string and string array objects, timespan and timespan array objects, and then you use indices inside square brackets to access elements of an array or a matrix. We talked earlier about FreeFlyer being 0 indexed. So if I want to access the first element of an array, it would be the name of my array and then a 0 for that 0th element. And then you can assign some value. You can assign an entire array using curly brackets, shown in the third example, and you can assign an entire matrix using square brackets. Note that to go to a new row, you use a semicolon inside of the square brackets. Timespan objects are used to store time values in FreeFlyer's nanosecond timing precision mode. These are properties such as epoch or elapsed time. You have the option to use either a literal timespan declaration or a static method timespan value. So you can specify days, hours, minutes, seconds, milliseconds, all the way down to nanoseconds. And the two different options here, you can see the all caps timespan and then the unit in which you're defining. Or you can use the static method, which has the methods associated with the timespan object. So timespan.fromDays and then some value. So you'll notice that using FreeFlyer script, there's lots of different options of ways to do things. We also include built-in functions for many common math operations. This includes things like the absolute value, the max, the cosine. We have orbit state conversion functions. So if you're looking to convert element sets or reference frames, if you need to convert times to different time systems, you can do that using the time tools conversions. You can convert calendar strings and variables to timespans and vice versa. The example shown at the bottom of the screen here creates a timespan 1 with a value of 3 days. So timespan.fromDays x is equal to 3. The second example will take a string argument. So January 1st, 2020 at 12 o'clock. We use the parse calendar date method to convert that string into a timespan. The opposite would be to use the convert to calendar date, which converts from a timespan to a string if you're looking to, say, report or put it in a file. All right, we've seen the step command. So once the spacecraft is configured, the orbit state and attitude state are propagating using that step command. You can step the spacecraft one step at a time. This is often done in a while loop, or you can step to a condition. So a built-in orbit condition like orbit apogee, an epoch, a user-specified condition such as the true anomaly is 150 degrees. You can also combine conditions using the and or keywords. When you're working with multiple spacecraft, one key to FreeFlyer is to ensure that your epochs are synchronized. This ensures that your data and visualizations are all evaluated at the same epoch. We do place the responsibility of keeping epochs synchronized on the user, and this is in order to provide flexibility and efficiency. So in the example above, you can see we have a spacecraft elapsed time for 1 day, so we're going to propagate for 1 day. We'll step spacecraft 1, and then we step spacecraft 2 to spacecraft 2's epoch is equal to spacecraft 1's epoch. So this is where we're doing that epoch synchronization. You also have the option for a while stepping command, which can be used to execute FreeFlyer script while propagating a spacecraft to an end condition. The spacecraft's propagator step size can be used to control the frequency that the script inside a while stepping command is executed. In this example, we're going to be stepping the spacecraft to the spacecraft's orbit apogee. And while we're doing that, we're going to put the spacecraft state into an ephemeris object, as well as visualize the spacecraft using a view command. We also have a while maneuvering command that works similarly, and this allows you to execute FreeFlyer script while a maneuver is being performed. So if you want to visualize something or likewise put the spacecraft state into an ephemeris file, you would use a while maneuvering command. We'll briefly go through lists and formations. You can create a collection or a list of any object in FreeFlyer. You can set the number of objects in the list and use indices to access each object in the list. So here you can see we're creating a list of ground station, so common objects, called DSN, setting the count to 3. And then for the first element, so DSN 0, again, that's 0 indexing, we'll set the display name to Canberra. A special type of list is a formation. So this is a special type of list of spacecraft objects, and it allows you to propagate an entire constellation with a single step command. You can visualize the formation using a single view or map command, and you also have the option to view each spacecraft as a simple point or as a 3D model. They can be initialized using a TLE. You can explicitly define the states in FreeFlyer script. You can use a RINEX broadcast ephemeris file or an SP3 precise ephemeris file. To access individual spacecraft in the formation, use the same syntax that you do for any other list or any other array that we've seen earlier. For procedures, FreeFlyer supports user-defined functions. We call them procedures. We place commonly used blocks of script inside a procedure, and you call a procedure from any point in your mission plan. You can embed a procedure inside a mission plan, or you can save it into a separate text file with the FF procedure file extension that then can be used across multiple mission plans, or you could share it with a colleague. You can pass any FreeFlyer object, so a spacecraft, a variable, any object as an argument into a procedure for input and output. And it organizes your FreeFlyer script for easier development, maintenance, and debugging. We can see a simple example here. We're going to use the define procedure command. This is going to specify the name of the procedure as well as the list of required arguments, and then the end procedure command to close the procedure. So we're defining a procedure called apply rotation. The objects required are spacecraft and variable. You would do some analysis, and then we would call the procedure within the mission plan, and we would pass in arguments from our the objects that we've created. So the object types must match the signature, but the naming convention does not have to. So we'll call apply rotation, give it some spacecraft and some angle. We've seen the commands for basic output, so the view command, the map command, the plot command, and the watch command. These commands are used to generate output very quickly, but they didn't provide us any configuration options. So we'll talk about the object windows themselves after we briefly go through these commands. The view command, as we've seen, is a 3D Earth fixed viewpoint by default. The map command is a 2D equidistant rectangular projection of the Earth, as we've seen. The plot command will display one or more series on an XY plot, and each series will use the same x-axis values. So in this example, we have the elapsed time in days on the X, and then on the Y, we have kilometers as the default unit size, but we're doing the apogee height and the perigee height in the same plot. The report command displays a data table of values onto the screen. So here you can see azimuth to a ground station as well as elevation. And this is easy to copy over or just display on the screen for you to look at while this mission plan is going on. So let's talk about the objects themselves. The report interface object is going to be used to collect data and text at various points within a mission plan and generate a single output file. This provides the option to append new data to the end of an existing file, and you use the report command to send data to a report interface, and the close command is used to release the lock on the file. So you can send data to things like a text file. You can do a CSV if you're looking to load into Excel. You have all different options for that file extension, and you can report those to those directly from FreeFlyer. All right, so we've seen the commands. On the left-hand side, we have the quick output commands, and on the right-hand side is the objects that provide more customization options. So view and map are equivalent to the view window object. Plot, monitor, polar monitor plot are under the plot window umbrella. Watch is a watch window, and report is a data table window. So instead of calling view spacecraft 1, you would simply call update view window 1 to send new data to any output window. That's just one example, but the view window object, which we would use in place of view or map command, allows you to create one or more viewpoints within each view window. So this is a 3D view, a 2D map, a sensor view, celestial sphere, star map, as well as the rotating, pulsating, and blockage diagram views. This allows you to define different display options for each object. So that includes things like the spacecraft color, font, line width, history, length, and icon, as well as upgraded surface textures and lighting, ground station and sensor opacity and projection height, and more. Some examples here, we have the sensor view in the top left, celestial sphere in the bottom left, a 3D view including coastlines in the top center, a 2D map with some country borders or political boundaries, a rotating pulsating view in the top right, a star map in the bottom right, and a blockage diagram view where the mouse is currently shown, third on the bottom. The plot window object can be used in place of the plot, monitor, and polar monitor commands. And this allows you to configure things like the plot title, subtitle, legend, grid lines, background colors, and series colors. You can control axis label and spacing. You can control display settings for each series, so the color, the type, the line style or marker style. And you can see two examples here on the right-hand side, where we've got the plot title, the legend, the different marker styles, as well as the coloration. So that wraps up the quick demos. I do want to call out one of the keys here is the documentation. So I tried to pop open the help file at various stages, but in addition to the help file, you have the sample mission plans. As I mentioned, there's about 225 sample mission plans, and they're separated out by the different guides in FreeFlyer. So a lot of what we covered today is under the spacecraft propagation folder, as well as the generating output folders and FreeFlyer scripting folders. Within the help guide itself, there are guides for spacecraft propagation, generating output, and FreeFlyer scripting, as well as other things like coverage and contact analysis, maneuver and target modeling. But in addition to the guides, each object, property, and method table for all the objects we covered, so things like the spacecraft or the propagator, have detailed documentation within the help guide. The appendix contains information on ephemeris and other data file formats, so I'll quickly pull that up before opening one last thing. So when we talked quickly about the guides, you can see for the spacecraft propagation, you'll learn about the spacecraft object, the different element types in FreeFlyer, the reference frames. Under generating output, you can find the plot windows, you can find the different view windows that we talked about. And then down here at the bottom is the appendix. So in addition to our things like our release history, you can find details on the ephemeris files we support and the data files that are used natively in FreeFlyer, things like the atmospheric model files that we talked about, as well as the geopotential files, which were covered briefly. So this has the source as well as some information on how to import new files if you're interested in doing so. We'll also talk quickly about the FreeFlyer users forum. So I've left the link here at the top. This is a dedicated website with a discussion board for users all over the world to learn about FreeFlyer from FreeFlyer team members and each other. So FreeFlyer users can ask questions about the tool or engage in conversations with other users in the forum. This is also an opportunity for you to showcase the projects that you're working on. We don't have a definitive date, but we're looking to have university students showcase some cool projects they've worked on at some point this year. So if you're interested in doing that, feel free to reach out to our team and also post some questions or teach some people some stuff on the forum. We want this to be an organic conversation. It's a great way to access the FreeFlyer team as well as different users across the globe. There's also the FreeFlyer University Guide. So this is a comprehensive guide written by students for students. This is designed to get new users familiar with the basics of FreeFlyer. So in addition to the sample mission plans that we have, if you're looking to learn how to build out something like a Holman transfer, this combines the orbital mechanics and astrodynamics side of school with the practical example written in FreeFlyer script. That's just one of the many examples that are designed in the university guide. And once you feel comfortable, there's the FreeFlyer certification program. Level 1 certification focuses on the fundamentals of FreeFlyer, and then Level 2 certification focuses on more specific topics within the tool. So things like coverage and contact and maneuver and targeting. Coming soon, we'll have optimization and orbit determination and plans to continue development on further levels of certification. That wraps things up for today. I know we're a few minutes over, but we did start a little late. Here's some contact information for myself if anyone's interested. And I thank you all for your time.